All right. Yeah. So, I mean, I just wanted to take just a quick moment to congratulate both Liam and Yuzhi on completing their master's thesis. Digital claps.
Thank you. Thank you so
Yeah.
much.
Yeah. And I know you both worked long and hard on these projects, and I, for one, am very much looking forward to hearing your presentations today. And so I'll briefly pass this on to Ani so she can share her congratulations as well.
Thank you. So again, welcome everybody to our fall semester master's thesis presentations. So I was just commenting about the fact that generally this is, we don't have a formal presentation in the fall, mostly because we just don't have the numbers, right, of graduates as we normally do in the spring. But we're taking full advantage of the remote format so that we can have more, be able to not just record this, but also have people who are physically not in present in Philadelphia be able to join and sort of listen in. It's a great pleasure for me to be able to kick this off, given the fact that, ROBO MSc degree program at Penn is sort of one of the highest rated and one of the most selective robotics master's degree programs in the country, if not the world. And so our students are always drawn, right, from very, very, it's a very competitive process to get in. And once it's in, we kind of put them through the ringer. And hopefully, right, they come out with what they consider to be not just useful, but also marketable skills. So given this, this is kind of, the thesis is kind of the culmination of their many their at least 2 years, if not more, toil. And just to sort of give you some perspective, right, these people, the students who complete thesis, this is sort of, in addition to coursework, they actually have to fit in time for the research and then be able to, not just do the work, but also be able to complete the document as well. So this is actually quite an accomplishment for all our graduates and the ones that have completed their work. So without much further ado, I'm going to present our first presenter, Liam. Liam is going to talk about learning formality from Japanese English parallel corpora. So Liam, I'm going to let you check to make sure you can share your screen.
Yeah, definitely check and see if that's working.
All right, I will check that. Everyone see?
Yep. So just to as you're setting up, I'm going to give everyone a quick sense. So this is going to be about 15, 20-minute presentation. We'll have a few minutes of Q&A afterwards from the audience. And then, so if you have questions, I will moderate. Feel free to, let's keep our microphones mute during the presentation. And then at the end of the presentation, what I'll do is I will moderate. Feel free to unmute yourself or type questions in the chat, and then we'll go from there, okay? So without further ado, Liam, go ahead and take it away.
All right, thank you. Okay, so this presentation is a little bit on the long side, so I'm going to go decently fast. I'm sorry in advance, but there's a decent amount to cover. Okay. The overview, I will start off by introducing the problem we're trying to solve, and then I'll go into what we've done with Japanese English parallel corpora, go into separating formality from topic, which is, I'll get into this, of course, and then I will conclude and talk about future work. All right, so let's say that you're a Japanese English translator, and you're working on a movie script. The line that you're working on is in a scene where an employee is talking to their boss. The employee asks their boss, have you seen the documents I sent you? As a translator, it's important to not just translate the meaning of the sentence, but also you need to make sure you translate the register of formality properly, or else it's going to come off as really offensive and rude. So when you translate this, there's two options. The option that has the X next to it is very casual, and the option that has the check next to it is very formal. As you can see, we use the humble version of the verb to send, and the honorific version of the verb to see. Honorific raises up the person you're talking to, and humble lowers yourself. This is really important in Japanese. I have another example that sort of demonstrates this. So this is an email from myself to my Japanese professor 3 years ago. And hopefully no one that's watching this knows Japanese because I'm cringing having to show this. My advisor convinced me to show this. What I wanted this email to sound like, oh, sorry. There's a bit of a feedback. Okay, cool. So what I wanted this email to sound like was like this. What this actually sounded like was something along the lines of this. Hey, yo, teach, got that homework done. Phew, Canvas link was down, so I don't know. I put the file here. Might be. What I'm trying to get at is this was incredibly informal. And when I came to class the next day, my teacher actually asked me if I thought he was a kindergartner and then imposed a mandatory must speak with formal rule in class. So that's when I learned this lesson. It is incredibly important to not just translate the meaning, but also the formality of sentences. Google translates close to doing this, kind of. So when I type in, how are you? It translates it formally, but I type in, hey, how are you? And it translates it informally. So that's good, right? Well, not quite. The verified checkmark actually means that a human had to go in and tell Google Translate that this was actually the correct way of doing this. So in fact, Google Translate really doesn't do this. You can imagine a machine translation system that would go something like, you take the English sentence and then you put it into a automatic formality estimation classifier. It tells you how formal it is. And then you can put both that tag and the sentence into machine translation. And then you would get out the proper formality sentence. And this has actually been shown by previous work to increase BLEU score, which is an accuracy metric for machine translation, by up to 10 points in certain categories, especially in the formal categories because formal is somewhat rare. So our goal is to improve that green box. We're trying to improve the sentence level formality classification in English. This is applicable in a lot of areas that aren't just Japanese English machine translation, but that's the one that's most relevant to me. So anyway, okay, what is formality classification? So let's start by taking an intuitive look at what formality actually means in English. So for the people watching, which one do you think would be formal and which one do you think is informal? Which of these two sides? Yes, I think it's pretty clear that, that to most of us, the left side seems pretty informal and the right side seems pretty formal. But how did we know that? Like what about these sentences told us that this was informal or formal? Well, so we can see a couple of surface level signs for formality in English. So, you know, proper spelling, proper punctuation, use of precise speech, higher levels of politeness, but these aren't really all that satisfying, you know? So these show us the surface level symptoms, but we want to know what the cause is, right? Like what actually is formality? It's not contractions, it's why do we use the contractions? Well, I'd like to propose that formality can be encapsulated within this idea of the speaker relationship. So there's a lot of different disparate definitions of formality across the literature, and a lot of them have very distinct, subtle differences, like the power relationship between the two speakers, the amount of shared information, but all of these have one thing in common, and that's that these things have to do with the speakers, the people who are talking, rather than the actual content of the sentence itself, and what the sentence means. We can think of an example where if you're watching a news story, the news anchor can talk about some event that's happened very formally, but then you can relay that event to a close friend in a very informal way while preserving the meaning of the sentences you say. So we can, through this example, we can see that the formality is less about what the sentences mean, but more about the relationship between speakers. We can use this idea to sort of frame our understanding of the previous literature on formality estimation and kind of see where we can improve stuff. So just really quickly, sentence formality classification is the task we're going for. Given a sentence, we want to predict whether it's informal or formal. There's generally two types to this. One is the binary prediction, and the other one is a categorical prediction, which is rate a sentence on a scale of -3 to 3. And there's some examples below. One simple way to do this, it was developed here at Penn, is we can take the log odds ratio of words. So we have a corpus of formal speech, so say a bunch of transcripts of the UN, and an informal corpus, i.e. some phone conversations. And we can take each word in a sentence and we can check, is it more likely to appear in the formal corpus or the informal corpus? We do that by log probability. And if it's more likely to appear in the formal corpus, we give that a score, more formal. And if it's more likely to appear in informal corpus, it's more informal, and then we average all of the scores and we get a formality rating of the sentence. The correlation that this gets with human annotators, for the words, it's okay, and for the sentences, not so great. We can do a lot better. This is a solid baseline, but we can do better. So the main way that this is done is, well, so I should say in 2016, Pavlik and Tetrault decided to decide once and for all what we use to classify formality. So they chucked a bunch of features into a big ridge regression classifier and tried to see which one of them would perform the best. A lot of these features, parts of speech, you know, the subjectivity of the word-to-vec is a representation of words' meanings. This did really well. It got Spearman correlation of 0.7, 0.75. It's still considered the sort of gold standard for what we should do with formality classification. Just take a bunch of features and then see what happens. But I'd like to propose that this result might not be all that it seems. So let's take a look at what features are indicative of formality by this classifier. So we see that n-gram, and n-gram is just, you know, sequences of specific words. And then word-to-vec, like I mentioned, is the meaning of the word in like a vector representation. And these are the two most indicative features for formality. Both of these two features are topic-related elements. They're about the meaning of the sentence, and they're not about the relationship with the relationship between speakers. Or I should say they're not stylistic elements, they're semantic elements. This is bad, as we've previously established. So how should we fix this? So I propose that we can use Japanese to fix this. So here's the overview of the approach that we're going to take. So we're going to take a Japanese-English parallel corpus. And now this is a corpus of sentences that are translated. So we have English sentences and we have the translated Japanese versions. We're going to put the Japanese version through a Japanese formality recognition machine, which basically checks to see what register the Japanese is in, formal, informal, or polite. It will give us a tag. And then we can just train on this English data. This is labeled data. And then we can train a sentence formality classifier on that labeled data. Importantly, these labels come from the Japanese registers. And the Japanese registers denote the speaker relationship, right? You use formal speech with someone who's of higher status. So this should be agnostic to the sort of issues that happened in the previous work. Okay, so in order to do this, we need three main components. We need the parallel corpus, of course. We need a good formality recognition machine, and then we need an algorithm to classify. So step one, we have to choose a parallel corpus. What would our ideal parallel corpus look like? Well, it should be large, preferably over 100,000 sentence pairs, and this is because the next largest formality dataset is 100,000 sentence pairs. So we want to be the largest, of course. We want it to be well aligned, which means the translations actually match each other. We want the translators that create the dataset to be experienced so that they preserve formality and they generally know what they're doing. We want the topic to be very varied, and we want there to be a lot of different domains of speech. And really importantly, we want to make sure that there's a lot of different speaker relationships in here. We want to make sure that, so for example, a corpus like Wikipedia corpus, there's only one type of speaker relationship there, and that's person who's writing a Wikipedia article, formal, who's higher status, and then you, the reader, lower status. There could be a lot of different topics talked about, but if there's not a lot of different speakers, then we don't get a good spread over formality. So what we picked for this project was the Japanese English subtitle corpus, and this is 3.2 million English to Japanese sentence pairs, and it was created by crawling different repositories for subtitles online, where fans of anime and manga can put their translations online for free. This was heavily filtered for alignment at both the caption and the document level. So does this work well? Does this actually accomplish what we want? Is it large? Yeah, definitely. Is it well aligned? Well, Japanese and English are notoriously difficult to align. I'll get into why this doesn't matter a whole lot, but suffices to say that formality is local to an interaction, not to the actual sentences. So it doesn't matter if the meaning is a bit different, as long as the same two people are speaking, the formality will be the same. The biggest issue with JESC is actually the lack of experienced translators. Since these people are fan translations, they tend to take a lot more liberty with their translations, and we'll see that later on. It definitely does cover a lot of domains, and it definitely has a lot of different speakers because we're talking about TV shows, and there's a lot of different characters. Okay, so the second component is the formality recognition classifier. Cool, so quick overview of Japanese formality. I talked a little bit about this before, but let's talk about it more formally here. So there are four registers. There's the plain register, used with friends and family or informal. There's polite, which is used with acquaintances. And then there's the two formal registers. At the bottom, you can see the conjugations of verbs. These are usually expressed in verbs. The polite register is often expressed by conjugations of verbs or different forms. So miru, which is to see, goes to mimasu. Iu, which is to say, goes to iimasu. The problem is that the formal register is most commonly expressed in alternatives to common words. They take the polite verb endings, but So goran ni narimasu is the formal version of the verb meter. This makes the formal register a little bit more difficult to classify than the polite register because we have to have a big database of all of the possible formal verbs. So previous work has done this problem by tokenizing Japanese and looking for a bunch of different verbs. As you can see, the amount of formal verbs they're looking for is very large. This is good, it gets decent performance, but it seems a little bit cumbersome, and I think we can do better, especially because some of these keys actually conflict with each other, and then some of the other keys just seem way too small. Like, there's no way that da doesn't appear anywhere else in the entire sentence. So we can do better. How exactly are we going to narrow down this list of keys? Well, so remember the goal. We want the Japanese sentences that are most likely to make the human translators write English formally, because at the end of the day, all we care about is the final formal English. So what we can actually do is do a little bit of a bootstrapping variation of this. So we'll take the parallel corpus, and we'll actually, instead of taking the Japanese, we'll take the English, put it through a formality classifier that was trained on manual data, get a label, and then we can train on Japanese. We're only going to do this once just to get a good idea of what is and isn't formal, what keys do and don't correspond with English formality. But once we do, we can kind of get a good idea of what we're looking for here. So if we rank all of the keys from the previous work, we can see that the informal keys they're kind of inconsistent. The polite register keys seem to be pretty consistent, and the formal register keys didn't even appear because they were just too rare. So it looks like we're going to go with these sets of polite keys, and I've noted by asterisks the keys that I'm going to go with. The final version, the final form of the Japanese formality recognizer is we string search on untokenized text. If a key is present, we label formal, and if no key is present, then we label informal. And these are the 7 keys that we chose. Okay, cool. So now we have that. Time to go do the sentence formality classifier. This is simpler than you'd think. I'm going to use BERT. BERT is very common, very popular. It's a pre-trained model, so you just download it and then you fine-tune it on new data, and then you go forward. Talking about BERT, I don't have too much time to begin with, so I'm going to save that for a different NLP presentation. Feel free to look it up on your own, but it is very good and very popular. Cool, so now we have all these components. So we put it all together. We run our Japanese formality recognizer. We get 520,000 formal and 2.28 million informal sentences. We discard the Japanese and then downsample. And that leaves us with 1 million English sentences with binary formality labels. So I'm going to call this the Japanese formality corpus. Even though it's in English, I understand it's a bit of a misnomer. So this is the JFC. Cool. So how do we evaluate the JFC? We should use the same algorithm, so we'll use BERT, and we will fine-tune it on JFC. We will also fine-tune it on other data sets and see which classifiers perform better. And if our classifier fine-tuned on our data set performs better, then our data set is very good. So the data sets that we're going to compare against, there's 3 of them. The first one is manually labeled formality data. So this is the data from before. Annotators give scores, we average the scores, we threshold it at 0, and then we have a data set. We have the Grammarly Yahoo Answers formality corpus. This is a corpus of parallel formal and informal sentences. So annotators were given informal sentences, asked to rewrite them to be formal, and then you have pairs of sentences that say the same thing, but are now informal. This data set is super popular, and a lot of people use it for style transfer. For our purposes, we will be taking out this pairwise relationship and just giving the sentences the labels for comparison. The third data set is an interesting one. There's actually been previous work done on something, approximating our work, but with German. So German has formal or informal register, but it's only present in the second person pronoun, so the word for you. So this data set, there is 55,000 formal sentences, and we downsample to get 67,000 sentences across both registers. Cool. So we're going to evaluate on the Grammarly corpus and the manually labeled data. Our evaluation on the Grammarly corpus showed that our Japanese English data outperformed both the manually labeled and the German English data. Now, this is an interesting result on the manually labeled side, but I'll save the talk about this for the second section. We also outperform GYAFC and German English on evaluating on the manually labeled data too. Note that I'm not actually reporting the performance for manually labeled data on itself, because that would kind of be unfair. Of course, it's going to beat our data, but point is that our method performs well on both of these tasks, on both of these data sets. It outperforms the other 2 on both. So takeaways here is Number one, it's definitely possible to train a pretty good formality classifier without any manually annotated data at all. This classifier is also good across domains. The technique to analyzing Japanese formality is fast, and it works even when the translations and alignments are of questionable quality. This technique can also be applied in any language that has Japanese translations, and you can get a formality classifier in any language. Okay, so why did the manually labeled data perform so badly? As you can see, the recall is really, really low, and the precision is really high. This means that we're barely getting any of the positive class, which is any of the formal sentences. This means that the manually labeled data is labeling almost everything in the Grammarly Yahoo Answers formality corpus as informal. Why would that be? Well, remember, so the manually labeled data was actually sampled from 4 different domains. The one on the far left is Yahoo Answers, and it turns out that it is by far the most informal on average out of all 4. So because of this correlation between Yahoo Answers like topic meaning material and informality, classifiers that are trained using this manually labeled data associate the actual topics that are talked about in Yahoo Answers with informality, not the style. The thing with GYAFC is that it took these informal sentences and told annotators to rewrite them to be formal. So they have the same meaning, but different style. And so the manually labeled data classifier sees the meaning of the sentence and doesn't see the style and says it's informal. So to confirm this, we use the same experiment that we did to get the keys to see what would be the most predictive words for formality in English. It turns out the most predictive words for formality in English, according to the manually labeled data, are America, of the university, investigation, government. All of these are from the news domain, and as we see, the news domain is by far the most formal. This pretty much confirmed our suspicion that there was a pretty big topic bias in manually labeled data. So despite the good performance, it seems as though there's still a lot to be learned for formality classification. Like we said before, formality is defined by the speaker relationship. This means classifiers should not use the meaning of a sentence as a predictor for formality, but it's impossible to normalize for this, right? You know, if there is a bias in your data set, your classifiers will be biased. And it's impossible to ensure that every single subdomain of your formality data set has an equal number of formal and informal, because you can always find a new dimension to group things by. So this is where adversarial decomposition comes in. So we did a bit of a proof of concept study. We wanted to take an input sentence and decompose it into meaning and style. The details of this architecture, I don't have too much time for. Point is that it takes sentence, splits it up, style vector and meaning vector. Does it work? Actually, yeah. So this is Grammarly Yahoo Answers formality corpus. The untrained vectors, so red dot means informal and blue dot means formal. Untrained vectors, kind of a mush. Style vectors, perfectly separated by informal and formal, and the meaning vectors are all kind of a blob. This is pretty cool. It would be much cooler if this worked as well for the other data sets. Reminder that Grammarly Yahoo Answers is a parallel corpus. The only thing that differs is the style. The meaning does not differ. In the Japanese formality corpus, there are still correlations. We can imagine that these clusters are probably from different source material. Same thing happened with manually labeled data. But I do have faith that this technique could be used in the future. The accuracy of the decomposed vectors actually goes up in proportion to the amount of bias that's in the data set. So GYAFC got a huge boost in performance from 62 to 96. JFC got a slight boost in performance, 6%, and then manually labeled data saw no boost in performance. And like I said, this is proportional to how biased the data set is. Anyway, takeaways, adversarial decomposition has a lot of possibility. I do think that if the technique is refined more, that this would be the avenue for making sure that our formality classifiers will generalize to new domains and we won't run into that problem that the manually labeled data has. Okay, to conclude, sentence formality classification is really hard. Essentially, for a lot of these sentences, it's an impossible task, right? Sometimes the formality of a sentence is just ambiguous and there's really not much we can do. But that being said, formality classification is far from hitting that ceiling. There's a lot of work to be done. We could run this technique with lots of other languages like Korean. We can attempt to do this in categorical formality. We can attempt to apply this to politeness. I think adversarial decomposition is the way of the future for formality estimation. There's a lot of work to be done. And these improvements actually really do matter. It improves machine translation empirically. We get better information extraction for polite sentences because they're more precise in their speech. Style transfer is predicated on having good formality classification, because otherwise how would you know if your style transfer model is working? So yeah, point is that it's a hard task, but there are a lot of benefits to doing it. And I think that there's a lot of room to improve. So thank you. Any questions?
Great, thank you so much. So at this point, we're going to open the floor up for questions. And let's see, I'm going to monitor the chat. But again, feel free to unmute and ask your question.
Hey, Liam, just want to say really great job. Super awesome stuff, really cool stuff. I have a quick question. When you were comparing the different data sets' performances, did you also make sure that the data sets had equal size? Like, I guess, how do you know that the discrepancies in your sense formality classifier were due to the data set being better versus the size of the data set?
So if you're talking about here, let's, hold on. Talking about the original here, correct?
Yes, correct.
Yeah, so are you asking, so the difference in performance on size, I actually did a study where I only fine-tuned on a subset of the dataset versus the entirety of the dataset, and the performance was pretty much identical. This is for the JFC and for GYAFC. So unfortunately, it looks like we're not able to take advantage of the 1 million size or the 100,000, 200,000 size of GYAFC just yet, because BERT is already, pre-trained with quite a lot of the information that it needs. So the fine-tuning on a small subset, the quality of the data matters a lot more than the quantity of the data. Does that answer your question?
Yeah, definitely. Thanks.
Okay, cool.
Great, thank you so much. So in the interest of time, I have, I think this was very interesting and I have lots of questions, but in the interest of time, I'm going to sort of, hold my, I'll take my questions offline with Liam. And thank you again, Liam. I'm going to now we're going to pass the baton to Yuzhi. And Yuzhi, if you can try sharing your screen.
Yeah, I'm trying to do. Okay.
Okay,
can you see
great.
that?
So, yep, I think we're good to go. So, Yuzhi Wang, so he's going to be presenting semantic segmentation, panoramic images with group convolution, and go ahead and take it away.
Okay, thank you so much, Annie. Yeah, so today I will present my master thesis, semantic segmentation on panoramic image with group convolution supervised by Professor Kostas. And we will have the following topics: introduction, related work, methods, experiments, and then conclusion. So first is the introduction part. And the semantic segmentation is a computer vision task in which we will link each pixel in an image to its class label. And we can think of it as a image classification at the pixel level. So to the right side, there is an example of a panoramic image and also its corresponding semantic segmentation. So on the segmentation, different classes labels are marked with a different color. And this example is taken from the 2D 3DS dataset by Stanford. And we'll also use this dataset in our experiments. So recently, panoramic images are becoming more and more popular for their large field of view and also good scene stability. But the power of traditional 2D convolution neural network cannot address the problem well due to the distortion had in the panoramic images. So let's step into the next section and take a look at some related work. In 2017, Su and Grauman proposed to learn the spherical convolution on the panoramic images and share kernel weights on they share the kernel weights only along the road to decrease distortion. But this method cannot maximally take the advantage of the pre-trained networks, since it only shares the filtered parameters along the longitude. Then in 2019, they proceed to introduce a learnable transform on the convolution kernel from perspective images to the rectangular projection according to the original location on the sphere. And in the UGSCM proposed by John in 2019, they project the spherical images into icosahedron with a triangle mesh, and then they introduce a new convolution and pooling kernels on the triangular pixels. And they also increase the computation efficiency by applying the linear combination of parameterized differential operators on the icosahedron mesh. And there is also another work done by Lai in 2017. So it could convert a panoramic image to a normal field of view hyperlapse. Okay. In this section, I will introduce our methods, including the multi-view UNet, which is our baseline model, and also the multi-view UNet with pooling, and most importantly, the group convolution UNet and the group convolution UNet with concatenation. We start from the UNet. So UNet is a classic deep learning model in the semantic segmentation task, and it is an encoder-decoder-like model. Consists of two parts. The left part is a contracting path to capture the context, and the right side is a symmetric expanding path that will enable the precise location and generate the mask for us. So the input to the UNet is a single image, and output would be the mask segmentation map. And our baseline model is actually to create multiple views using projections on multiple tangent planes, and then put it to the UNet. So recall that we could recover the panoramic image back to the spherical image. We then picked specific points on that sphere and then projected the spherical image to the tangent planes. So all those tangent planes images will become the input to the UNet and be processed independently. And in the end, we'll collect the semantic mask for each tangent image, and then we'll stitch them together to recover the final result. So this is an example showing our different views. So the left figure shows a sphere, and you can see 24 different frames on it. Each frame actually represents a view. And where we will project the spherical image to its tangent, corresponding tangent plane. The orange arrow indicates the optical axis, and the blue arrow is the x-axis of the tangent image, and the green arrow is the y-axis. And the right figure shows how we make the projection. It's called the mnemonic projection. So for each point on the sphere, we will connect it with the center, and the point where the ray intersects with the tangent plane is the corresponding location on the tangent image. So we will first build the correspondence, and then we'll use interpolation to generate the tangent images. So for example, here is the raw image from the 2D 3DS dataset. And here is our cropped 24 views, and this is a corresponding input to the UNet. And here we create 24 views, and for each view, we only keep local information so that we could mitigate the distortion. And these views are also overlapping with each other so that we could be guaranteed that we cover the whole image. So now the good things about the multi-view UNet are that it could mitigate the deformation on the panoramic image. And it also takes advantage of the pre-trained UNet, since the vertical direction doesn't change really much. But we're processing each view like independently, though they come from the same image. So one idea of the possible improvements is that, could we add global information to it? And the answer is yes. We can use a pooling layer to extract the global information and then concatenate the extract feature map with our multi-view feature maps. Let me show you in this figure. So on the left side, we have our multi-view feature maps. And after the pooling layer, we'll get one single feature map. And this feature map will contain all the global information. And then we concatenate it after every original feature maps. This would be, so this pooling layer is applied to the code which gets from the encoder part of the UNet. And then the feature maps will have double the amount and be fed into the decoder part. but we will control the network is still output 24 masks, and then we recover the semantic segmentation mask for the original panoramic image. Okay. So here's another way to integrate global information, the group convolution. So group convolution was introduced into deep learning by Cohen in 2016. And recall that the spatial convolution is defined as the first equation here. But to the group convolution, we'll associate our views with group elements in a finite rotation group. So like the spatial convolution, we could write our group convolution in the second equation. So the only difference we need to make here is to change the operator for the spatial variable to the operation to the group element. So you could say the y minus x here is changed to inverse of g times y here. And as we mentioned, we are working on a finite rotation group combining with the spatial convolution. We'll have the third equation here. It is actually the convolution for the cross product group of the rotation group and the translation group here. So the S and T are elements from the translation group, and the G and H are elements from the finite rotation group we have. And in our method, each view is associated to an element in the rotation group. The rotation group we use here is a C12. So all the rotations are with respect to the azimuth axis. And here we have a Kelly table that shows all possible results of the operation between group elements in the C12. So this will help us to calculate the corresponding kernel for each feature map. Now this is a key part. This shows how we do the group convolution layer in our model. So again, to the left side, we still have we'll have 12 feature maps. Each feature map represents a view, and we also have a kernel with size 12 by k by k. So it actually consists of 12 different k by k spatial filters. For each of the group elements, we will apply it to our kernel. And for the translation group, it will cause a movement of the filter in the feature map. But for the finite rotation group, it is actually equivalent to move to the next permutation of the 12 filters. And we implement the spatial convolution for corresponding filters and the feature maps, and then sum them together to get the convolution result of one group element. We then use this for all 12 group elements and get 12 feature maps results, which are shown on the right side. This is also done in the code part of the UNet. And another key point here is that we could start our training from where the baseline model ends. So recall that the only difference from the group convolution model and the baseline is a group convolution layer. We could design our kernel so that after the group convolution, the feature maps will not change. The way to do it is similar to how we do it in the spatial convolution. So when you come up an image with a kernel full of zeros, but has a 1 in the center, the image itself will not change. So when we do the group convolution, similarly, we will initialize our kernel so that all the kernels, except for the filter that is corresponding to the current feature map, will have 0 values. 0 values are represented in the gray color in the figure here. Yeah, and this filter is also full of zeros, except for the center location. So in this way, we could start from where the baseline stops and continue to train. And this means that the baseline is just a special case of our model. So it is very likely for our model to outperform the baseline. And similarly, we could make some improvements here. We could concatenate each feature map results after the group convolution. We concatenate each of the results after its corresponding original feature map. And this is also done after the encoder part. And in this case, the feature map results will have double the amount, but we will modify our decoder part. So the output, final output will still have 24 masks, and we recover our final result from there. So in this slide, this is our one example of our recovered prediction and the corresponding ground truth semantic segmentation mask. And this is a same example, but with 24 views. So left is a raw output we have from the network. The right is the ground truth. And then for the experiments, we have two metrics to evaluate the performance of our models. The first is a mean pixel accuracy. It is the accuracy for correct classification for each pixel across all class labels. And the second is the mean intersection over union. It actually represents how much the predictions are overlapping with the ground truth. So here, this table will show the results of our experiments. Among the models, we compare our group convolution UNet model with pre-trained multi-view, which is the highest performance. So the UNet here is, we directly apply UNet to the task. FCN8S is a classic fully connected convolution networks. And the point net is we make every pixel a point and apply the point net plus plus. So spherical CNNs will have the convolution on the icosahedron projection with triangular mesh grid. And our baseline model multi-view UNet here achieves 51.93% mean pixel accuracy and 36.08% mean RU score. So in comparison, our group convolution UNet with pre-trained multi-view increased that by 7%, around 7% on the mean pixel accuracy and around 5% on the mean RU score. So here comes some analysis of the results. Our model with a pre-trained multi-view could reach 59.49% pixel accuracy and 41.17% RU score. And our model outperforms the baseline multi-view UNet in both the metrics. But the pooling and concatenation method doesn't improve the performance doesn't improve the performance in the experiments. And our model could take advantage of the pre-trained network and start from training from where the baseline model ends. So the results also prove the effectiveness of our group convolution layer here. And there are actually some possible next steps we could try. So first, we could try to get more views. And in the experiments, we use in total 24 views, but actually we could use more. The second is that we could have the group convolution at different levels. In the experiments, we only applied it to the code level. The third thing is that in the experiments, we only have one layer of group convolution, but we could try with more layers. Last thing is that in the experiments, we use naive cross-entropy loss, but we might want to check some other loss functions we could use. So thank you so much today. I would like to express my deep gratitude to Professor Kostas, my research supervisor, for his patient guidance and constructive advice. And I would also like to thank Professor Annie Shi for her review and suggestions. I would like to extend a grateful thanks to Yingsheng and Dr. Carlos for their kind help in this work. And thank you to everyone who helped me and attend the presentation today. Thank you so much.
Thank you, Yuzhi. So let's open the floor up for questions.
Yes, let me say first that it is very moving to see both Liam and Yuzhi here. After I have them both in my class, and Yuzhi was also later TA. And this is really always really cool to see people from your class do great research. Yuzhi, great. I mean, both of you, we had great results. Yuzhi, that's actually, we should try to publish this. This is great results, and also the increase, the 7% increase is quite significant. Can you show again the difference between pre-trained like tangent views and the trained one?
Do you mean the results?
Yes. Yes, right. So group convolutional unit without pre-trained multi-view, you mean that for each tangent view, it's trained at the same time with the group convolution?
Yes, so in the group convolution unit without the pre-trained multi-view, we will not start from where the multi-view unit ends. We will start from the pre-trained unit and add the group convolution and trains from here. Yeah.
I see. But in both cases, for the single views, you start from a pre-trained like Mascar CNN, right, or something like this.
Unit. Yeah. In both cases, we will start from a pre-trained unit. Yeah.
On both cases. Yeah. Okay. That's great. I have to switch to a proposal defense in electrical engineering, but I really appreciate your work, Yuzhi, and let's get together. Also, I thank Yuzhi Wang for really co-advising on that. Let's get together and talk regarding a paper.
Okay, thank you so much, Professor.
Great. Any other questions?
Yeah.
So I have a quick question, Yuzhi. I'm trying to sort of get an understanding. So when you actually pre-trained it with the multi-view, you took the original panorama and then you cut it, right? In such that, did you, I guess, have you guys thought about attempting this with actual sort of straight, with the, instead of a panoramic camera and actually using like a regular camera and actually taking the actual multi-views, right? And so you would have to have an array of cameras in addition to that panoramic camera. And the only reason is because that if you took the original raw panoramic image and you sort of, you chopped it up and did this sort of flatten things out, rectify each of them individually, there's potentially the introduction of errors, right? From that sort of fixing of the projection. So do you think that somehow that might improve just by doing, having proper multi-views rather than sort of the massaged, multi-views from the raw data set? Do you think that would change, provide a significant change in the results?
Well, I'm not quite sure if I understand the question correctly. So here we have the panoramic image and we recover it back to the spherical image and have multi-views and only crop a local patch of that window to train it.
Yeah.
But sorry, what is the other?
So the point is, rather than cropping, right, from the spherical image, is actually if you actually had raw data that was from a sort of proper, rather than a panoramic image, you actually have raw data from a non-panoramic, right, image effectively. So you would have less distortion, the raw data itself will have less distortion because you would actually be working with a limited field of view camera. And so those kinds of so I guess the point that I'm trying to make is more just the fact that, it seems like there's layers of errors being added, right, by doing this, taking the panoramic images, changing it into this, and then cropping, right? And so there's there's noise that is getting added to the training data set, and potentially you can remove that if you simply just had, the multi-views, right?
I see. Yeah, that is also, I think that is also a good try. We could try that, but I'm not quite sure if that will cause some like expensive computation there. Yeah, but we could give it a try. Yeah.
So I mean, I think it's an interesting, it's definitely an interesting way of thinking about it.
Yeah.
Great. So thank you so much, both of you.
Yeah, thank you.
Unless there's more questions from the audience, So this will conclude our fall semester master's thesis presentations. So I'm going to ask the audience to please join me again to congratulate and thank the presenters for a great job, and good luck in all your future endeavors.
Yeah. Great work, guys.
Yeah.
So make sure you get lots of rest.
Thank you.
Over the holidays.
Thank you so much.
Well-deserved rest.
Thank you.
Stay safe, and
Yeah.
Happy New Year. We'll see if we see you guys. We'll see you in the new year. So.